is from this application. And it's going to talk about extending hardware characterization theorem.
All right. So, let's see. Just to get you started here, let's warm you up with some ideas here. So what we're going to be talking about is we're going to be talking about, I believe the description I gave was something about continuous rigid motion invariant finitely additive measures on convex sets. So, whole pile of words there. So let's get you familiar with this. Let's get you another context in which you might be aware of this. So let's talk about measures. Okay. Usually when you talk about a measure, you're talking about a countably additive measure, but we'll get to that. And okay. So let me step back. I'll put the buzzwords here. All right. Okay. Basically, all a measure is, think of something like volume. So we're dealing here, we'll be thinking here in n-dimensional Euclidean space. Ooh, that's another buzzword I should put. Okay. So let's do some examples here just to fill you in there. So for instance, okay, we've got volume. So volume is actually, well, let's look at the properties of volume. If you have two things, okay, if you have two sets, I had some sets here, okay, just some random sets here, okay. Volume of this is 5, volume of this is 7, what's the total volume? Close enough. Okay. So basic property of volume, you learned that when you were, I don't know. But if you take two things here, the volume of A plus the volume of B, is the volume of their union. That's the basic idea of a measure. So right here, I'll use a fancy word, I'll use a fancy U symbol for the measure. Although that's if they're disjoint. So since we're mathematicians, we might think, well, what if these sets overlap? Well, what do you do? What do you do if the sets you're talking about overlap? What do you do?
Subtract.
You subtract the
Overlap.
Yeah, you just subtract the overlap. Okay? This is finite additivity right there. That's your basic property of volume. So, a measure, we're thinking basically some kind of volume here. That's a finitely additive measure. Now, regular volume, okay, is actually more powerful than this. It's actually countably additive. So you could actually say, if you have the volume of a whole bunch of things, so I'm not going to write infinitely many things, I'll just use the union of a whole bunch, infinitely many, countably many of those things, is just the sum of the volumes, even if you've got infinitely many of them. And for this, because we really don't want to have to worry about overlap for infinitely many objects, we usually just say, here, just one. That's countable. All right. So, invariant, that just means if we move the object, we should get the same stuff, right? If you move an object, you get the same volume. So, I guess I should use mathematical type symbols here. So if T is a translation, and eventually put it in space, it's a symbol there, then the measure of translation of this is the same as the measure of the original set. Okay. And you could do the same thing if you had some sort of rotation, reflection. Okay, so you can have translation invariance, rotation invariance, reflection invariance, all the usual rigid motion of space. You move your book, it still has the same volume. So this is basically what we think of. And continuous, loosely that means if you add a page to your book, that you only add a little bit of volume, right? But I'll define that a little more precisely in a moment because we want to make enough. Because when we look at this in the finitely additive case, things change a little bit. Okay, so that is the basic idea. We've got a finitely additive, we've got our basic properties of volume. In the countably additive case, let's see what we know. What in the countably additive case, there are no other measures. You're basically stuck with volume. But so this is the one that you always end up using in calculus class. You're just your standard measure of space. But when we move to finitely additive measure, the problem is that you can have lots of you can have all those little flaky bits that you have here, and if you don't want them to count, then you have to count them as 0, and so the volume is okay. But with finitely additive measure, you got some choices. So let me show you. Now the other catch when we're dealing with finitely additive measure is that we're not going to be able to do calculus. We're not going to be able to do calculus stuff as well because we can't do infinite limits of sets and assume it's going to come out to be the same thing. So we have to fudge. So that's one reason that I'm going to have to explain continuous and adjust that a little bit. And the other thing we're going to do is work with some nice families of sets. So say convex sets are a reasonably nice thing. If you want to do unions of convex sets, that's fine, as long as you don't, don't try countable unions. Finite unions of convex sets will work fine. So convex sets, you remember, all that means is if you take 2 points, x and y, in the set, then any point in between x and y is also going to be the set. So you can take some kind of average. You can take some kind of average of the points. Okay. So I think I've explained everything except continuity. So the question is, what does this? So for countably additive measures, there's only one sensible measure. There's basically the volume. So your measure of your set is some constant times the volume. For finitely active measures, okay, and I should put continuous. Okay. Finitely additive. Okay, and I put in continuous again, so, okay, let me tell you how continuous works. If we got 2 convex sets, we need a distance here, and here's is so the distance between 2 convex sets is going to be basically their overlap. Or, I mean, the amount, colors will be better. Here we go. So if I have a set K and another set L, the distance is defined to be the worst case scenario for getting from K to L or from L to K. So from this point, looks like, so from K to the closest point in L, or from L to the closest, from L to any point in L to the closest case at K, take the worst case scenario. So here's what's that's the formal definition. Basically, just take the worst distance between one set and the other set. So that has the right so that's distance. So continuous just means once we have that, we can define we can say K approaches F, so we can have a sequence here. If we have a sequence of sets, we can say it approaches another set if the distance between it goes to 0. And then now we can define continuous. That then if the k's are approaching the limit, then the measure should approach a limit as well. So it's a long way, it's a little of a ways around from our usual understanding of continuous, because we have to make sure that we're defining these guys. And the other thing, of course, is that these have to still be convex sets, because we're only defining the measure on convex sets. So now I've officially defined that. So this is a fair question to ask. I don't know if I don't expect you to know an answer, but I'd like to hear a guess here. How many finitely additive continuous translation invariant measures do you think there are? Take a guess. One? Good guess. Okay, we know there is one, right? This guy up here, the volume will still work. Can you think of any other finitely additive measures? Well, here's one we could use. Give you kind of a trivial example, is we could just define the count to be 1. So here, okay, that works. If we have two sets, basically we're just counting whether they overlap or not. So if we have two sets, A and B, measure of their union is 1, 2. If they overlap, then we'll get measure of A is 1, plus measure of B is 1, minus the measure of their overlap is another 1. So this just counts how many distinct sets you got. That's not a very interesting example. If that were all there was to it, we wouldn't bother with this. Here are some other examples. Perimeters. We talked about it, that in high school, but never came up with some fancy formalization type stuff for it. So let's check this guy. Let's check this guy out. If I have perimeter, okay, that's clearly invariant again. No matter, that's translation invariant. Rotation, reflection, yeah. Does that too, even. So perimeter will work. What happens if you add two sets together? Well, if I take A's perimeter, I add a set B. If it's different, it just has a different perimeter. If they overlap, that's the interesting case. Then I take perimeter of this, plus the perimeter of this, minus the perimeter of the union. So I count everybody once on the outside and nobody on the inside. So perimeter is a finitely additive measure. So we're actually getting something out of this. Okay? The countably additive stuff really throws you, though. That's why it doesn't work as a countably additive measure. Is basically you can have a lot of little, again, those little flaky bits we'll get to. You can't take the limit, but this works. So perimeter, once you got that, you can probably think of another example right now.
Length?
Length? Yeah, that's kind of a that's kind of like the volume. That's really a one-dimensional volume. But I'll list that. So length is kind of, I'll list that even though in a sense it's already on this list because we can. I do have something I'd like to talk about. Okay. Can you think of another, maybe a three-dimensional example?
Surface area?
Surface area, yeah. Okay. So how many examples do you think there are now?
More than one.
More than one. All right. So let's see. Anyhow. I'll move more quickly through this. So basically, these guys, anyhow, here's the upshot. Here is I do need to say, you can come up with some really weird examples. There are lots of examples here if you only have translation invariants, but I don't want to linger with that. So move on here, and I'll say rigid motion invariant. Okay, and So here's the theorem. These guys here are actually pretty much the measures. So more specifically, we have one of these, and we have one measure kind of like this in every dimension. So if you want to measure in n dimensions, you'll have an n-dimensional measure, which is your volume, and an n-1 dimensional measure, more or less corresponding to perimeter or surface area. Then a couple other measures, which I'll explain in a moment, and then a zero-dimensional measure that goes down to your counting measure. Any measure you like, any finitely additive, continuous, region motion invariant measure in a dimensional space comes down to just those n+1 measures. So I should explain these, and I should also try and give you just kind of a brief So first let me define, okay, so. Let's do a really special case of that growth. Convex sets are maybe a little too hard, so let's do really, let's make it even simpler, and let's just do boxes. So let's do boxes parallel to the axes. So things like this. So we'll just stick to parallel to it. So we'll just stick to the case of parallel to axes. And that also means we're going to have to limit our rotations to just swapping coordinates so that they always stay parallel to the axis. So, put the bricks like that. And first define the measures. If I have a box like this with, let's say, edges L1, L2, and so forth through Ln, then measure 0 of this box is 1 as before. The one-dimensional measure, how would you make a one-dimensional measure of a multi-dimensional object? Well, one way to do it is just to add up the edges. Okay, and then you have a two-dimensional measure. Add up all pairs. The n-1 dimensional measure will take all the faces, all the n-1 dimensional faces here, as you can see. So here L1, L2, this face, top face L1, Ln, last face L2, Ln, all the n-1 dimensional facets. So this roughly corresponds to surface area, except I'm only taking one side of each box instead of both. Scaling factors don't really matter because they get absorbed into our arbitrary constant. We can always double or half our surface area. And then the last one, of course, is our volume. So that's our idea. And now, let's see. What these guys are. consider a simple case where the measure has value 0 on subspaces, on n-1 dimensional subspaces. In that case, okay, so we won't have to worry about n-1 dimensional subspaces. In that case, we'll just take a big box, take a unit box, n-dimensional unit box equals something. Whatever that is, it's just an arbitrary constant factor, and I haven't picked a normalizing factor, so I'll make it 1. So with that normalizing factor, this out to be the volume. Let's see if it, well, let's see, because this guy is finitely additive, we can chop up this box into finitely many pieces. And because we don't have to worry about n-1 dimensional subspaces, we don't have to worry about the intersections anymore. So we'll just take this box, chop it up into, chop some parallel lines here, slices there, and just slice it up, if you like, into, let's say, m pieces that way, but m by m pieces that way. And so now, all these pieces are identical. So the box, size 1 over m on a side, and that has, all those are the same, so we'd have 1 over n to the m to the m. All those boxes have the same piece, so you chopped it up into a bunch of pieces, and now just glue the pieces together to get any size cube you want, as long as it's got dimensions that are a multiple of m, multiple of 1 over m. So you can do k over m, l over m, r over m, so forth. So you can take those little cubes and glue them up to make any size you want. And so far it's the same as the volume. And so we can do that for, basically that'll work for any rational number. And now we can use continuity to say for any box at all, no matter what the size. Okay. So you can see here, if you look closely, what the trouble is going to be if you try to generalize this to arbitrary convex sets. The angles are going to be a little bit nasty. The angles are not going to be nice and square, so you can't chop it up into same size pieces. You're going to have to use that continuity a little more carefully as kind of a crutch to substitute for the fact that you can't just cut things into infinitely many pieces and take the limit. So, but it does in fact work out still for convex sets that a simple measure has to be 1. And now, once you have that, you can proceed by induction. So, in general, take an arbitrary measure mu, and take a look at the first type, and just take a hyperplane, any old hyperplane, and cut your box. I'm stalling out here. I'm not putting. Basically, what you do is you do an induction type argument. You slice the box. On that n-1 dimensional case, we can assume it's true that the intersection is in. You can chop things up. The intersection is in n-1 dimensional space. You can assume that it's true by induction, the measure on the subspace. So that tells you what you should do for your subspace, and then you can put it back together. The remainder, if you subtract out that step, has to be simple and has to be long. So that's roughly the argument, but I don't want to linger on that because it's not an effective use of your time. Okay, let's see, time-wise.
I think sometime.
Yeah, I think we should draw.
We should start here.
Okay.
Okay. Any questions to Jason? And okay, let's thanks to Jason again.